I'm Professor Ron Smith from the Department of Geology and Geophysics, and if you're in the right place, you know that this is the course called The Atmosphere, the Ocean, and Environmental Change. There's a lot to talk about today. If some of you are shopping, I want to be sure you get enough information about the course to make your decision about whether to take it or not. And for those that are definitely in it, I want to get you started towards some of the course material that we have in this course as well. So as I will usually do in the mornings, I'll have some notes in the upper left there, and I want to run through some of those. This is just informational stuff, logistical information about the course. There was some confusion about this. The lab is required. So everybody that takes this course takes the lab, and everybody that takes the lab takes this course. You get graded separately for the two, but the two are really, the subject material is merged and coordinated in a certain way, so you have to take both of those. That means when you're signing up for the course, be sure to sign up for the lab as well. It has a different course number. For example, EVST 201 is this course, 202 is the lab. Or if you've signed up under geology, it's 140 and 141 is the lab. Now, we also, the classes server, they're separate sites, so be sure to register on both of those, because I'll be posting information about the lab on the lab course number. Now, the labs aren't going to start actually till week 3, so we're not going to do lab section signups yet. But I will tell you that the labs are on Monday and Tuesday afternoons. There's 4 sections altogether, and you've got to be able to fit into at least one of those, and we hope more than one, because we're going to have to even you out. But those labs are at 1:30 and then at 3:30 on both of those days. So we'll be doing those lab signups next week when you have a better idea of what your schedule is like. But try to keep those Monday and Tuesday afternoons open so you can fit into one of the labs, because if you can't take the lab, you can't take the course. Let's see, there's already a problem set posted on the classes server, and it is due next Friday, a week from Friday. And you may ask, how could I have already posted a problem set when I haven't given a single lecture about the course? Well, that's because this particular this particular problem set is kind of a warm-up. It's got questions on there that you can do with an elementary knowledge of high school physics, and I'd like to get you started on that, both because we need you to be fresh and familiar with those subjects, but also those of you that don't have a good background might want to use that as a guide as to whether this is the right course for you. So take a look at that problem set as soon as you can, and if you have any problems with it, talk to me, talk to your TAs. Speaking of TAs, let me see if I can introduce them to you. Ravi is there. Jennifer is there. Is Meng here? Meng is right there beside them. And Srikanth. No Srikanth today. Okay. And by the way, Melanie here on the left, on my right, is going to be helping with the taping transcripts. So we're going to have this course taped, and I'm afraid they're not going to be, these tapes are not going to be available to you during the semester. There's too much of a lag time, I think, to get those to you. But I don't think it'll be a problem in class. One thing I want to mention, though, this course, well, it seems like we got a pretty big class here, but still, even with this class, it's a very convenient room and a very convenient class to have a lot of discussion, questions, answers, and so be prepared for that. Don't be shy about asking questions, and I think that'll really add a lot to the course if you get in the habit. If you've gone for a period or two and haven't asked a question in class, you should ask yourself why, because it's probably not the clarity of my lectures. It's probably that you're just reluctant to put your hand up. So try to gauge this a little bit. And if you're asking too many questions, which hasn't happened yet, but if it happens, I'll tell you about that, and we can scale it back. The textbook is in. I went down to the bookstore yesterday and I saw it there. Didn't look like they had that many copies, but But I should mention that if you get a copy that's an edition or two old, that would be okay. And you might be able to really save some money by doing that. But get that book right away, because you're going to need that starting immediately. And if you have to order it online and it's going to take a couple weeks, that's probably not good. So get that coming to you. But anyway, the book is this one, Essentials of Meteorology. And a word or two about it. Yeah, well, it's a descriptive book primarily. It describes things that go on in the atmosphere and the ocean. And that'll be really great. That'll supplement what I do in lectures. The course, however, is more quantitative than this. And the quantitative material will come from my lectures. And you'll be working on the quantitative side of the course every week with these problem sets. So try to understand that you're going to be reading this to get the descriptive material, and you're going to be working off my notes and the problem sets to do the quantitative material. I wanted to mention that final exam date, because you know these exam dates cycle through. Yale tries to be fair in how they assign exam dates to different courses. And last year, our final exam was on the first day of exam period. Well, we cycled off, and now we're on the last day of exam period, December 17th. So if you're booking flights home, please keep that in mind. You have to be here on, I forgot what day of the week that is, but that's the last day of exam period for this course. Any questions so far? So, what's this course all about? I would say a lot of the course simply has to do with how the atmosphere and the ocean work. How does the air and the water move and mix? In the atmosphere, that's the winds. Also storms. How do storms? We're going to be talking about, in some organized way, I hope, the different kinds of storms, thunderstorms, frontal cyclones, tropical cyclones, and so on. So we're very interested in the basic physics of how the atmosphere and the ocean move. And for example, in the atmosphere, we're going to be studying clouds. How do clouds form? What is a cloud made of? And why do very few clouds precipitate, but some do? We want to ask that question because it has to do with climate, which brings me to a big part of the course is climate. Climate is defined usually as kind of average weather. I don't like that definition. I'll give you a better one when we come to that section of the course. But we certainly want to understand how climate varies around the globe. Why does Central Africa have a different climate than Connecticut, which is different from Southern California, which is different from, well, any place? There's a distribution of climates around the planet that controls how people live, how they do their agriculture, how they live their daily lives. We really want to understand that. That's a key part of this course, is understanding the distribution of climates and the impact on human beings around the globe. And of course, once we understand that, we can then go on to the subject of changing climates. How have climates changed over the history of the Earth, and how might they change in the future? So that's and of course the human impact as well. How have humans not only how climate impacts humans, but how do humans impact climate is a subject of increasing importance. So, questions yet? All right. Now, I've already mentioned this, but the way you're going to be studying this course, there are about 5 or 6 different things you need to be looking at for sources of information. The book, my lectures, which are more quantitative, the problem sets, which are quantitative. We're going to have 3 exams during the semester. Now, why am I listing that as something you learn from? Well, of course, you'll be tested on these exams, but I think you can also learn a lot from taking these exams. Through the lab, you'll be having lab exercises, including a field trip, getting up on the roof, launching balloons, measuring things in the atmosphere. You'll learn a lot from doing that. But the one thing that I can't control, it's entirely in your hands, is to develop a new habit of observing the environment as you walk around. So, for example, when you walk to class every morning, and for some of you it's a good walk, instead of just, turning on your iPod or zoning out, start to look up and around and try to figure out what's going on that day. What clouds are up there? What direction are they moving? What direction is the wind blowing in? Are there clouds at different altitudes moving in different directions? That's really an important thing to note. So that's a new habit. Now I want to tell you something about this, because you're all online several times a day probably. And let me see if I can just give you some good sources. I put this little document, oh, I lost my control here, wait a minute. Yeah, I put this document up on the classes server last night, so you have it there. But when something interesting is happening in New Haven, like happened last weekend with Hurricane Irene, I love to go on to these data sources and follow along and see what's happening with this storm. And of course, you don't have to do it that way. You can tune in to the television. The television weather guy is more than happy to give you his or her interpretations of what's happening with the weather. But you don't have to be satisfied with that. You can go to the data itself. And that's more fun than just listening to someone talk about it. So a few sites that I find really useful. One is this Tides Online site. Most of these are .gov. They're government sources for this. Now, you can go to coastal cities all around the coast of our country, but what I've done here is go to the New Haven one. And let me darken this a little bit so you can see that better. There's time on this axis and feet above mean low water. So this is the record of tides for New Haven Harbor. It's at the Coast Guard station right on the east side of the harbor there. And the blue curve is what was predicted for the tides based on the moon and the sun, right? The moon and the sun produce, their gravitational pull produces a tide in the ocean. Here in New Haven and most places around the world, it's a semi-diurnal tide. That is to say, it's a twice-a-day tide, 2 high tides and 2 low tides, and that's what you see in the blue curve. The red curve is what's actually measured. They've got a water level gauge there, and as it goes up, they record that. And now this date goes back to the 28th and the 27th, which was last weekend. And what you see here is that the seawater level rose quite a bit above what was predicted from the normal tides. And of course, that's what's called the storm surge, right? So as Hurricane Irene came up the coast and with the winds blowing counterclockwise around it, as it approached, the winds were from the east. In fact, that's on this curve. I'll show it to you in just a minute. Well, that wind from the east pushed water into Long Island, and the water level rose. And they've subtracted one curve from the other to get the green curve. So that's the difference between the observed water level and the predicted tide level. And you see that it rose about 4 feet above normal and then dropped a couple of feet below and then came back to normal. So that's a typical example of what happens with sea level as the hurricane comes up. Now, here's the wind data. It's too small for you to read from the back, so I'll try to walk through it. The same time scale is on the bottom here, spanning about 3 or 4 days. This is in knots, which is a traditional unit of wind speed. Unfortunately, it's not the one we'll use primarily. We'll use meters per second, but Knots is a traditional speed. A knot is a nautical mile per hour. So it's kind of like a mile per hour, but a little bit greater. So the wind speed increased as the Hurricane Irene approached, and from the little vectors there you can see the wind was from the east. It reached a peak of about 30, 32 knots, and then as the storm moved away, the wind speed decreased, but then the wind was from the west. Remember, so just to sketch this out if I can for a second. So here we are in New Haven, and the cyclone is like this. Winds going around in that direction. As it approaches us, the winds are going to be from the east, and then as it passes by, a day later, it's up here, the winds have the same direction around it. Suddenly the winds are from the west. So you're seeing that pattern there. And then, of course, that's what's reflected in the storm surge. First, it pushes water into Long Island Sound, then it pushes the water back out of Long Island Sound. So it's not too complicated, and the data is right there for you to see. Uh-oh, what happened there? Here we go. So here's another one. If you go on to water data USGS, that's the United States Geological Survey, and hit on the Quinnipiac River, which is the main river that comes down through New Haven. There's 3 rivers. We're going to do a field trip along the Quinnipiac as part of Lab 2 or 3, so you'll learn a lot about the Quinnipiac. But I went on just after the hurricane to get this data. This is the river discharge. Again, it's not in a metric unit, I'm afraid. It's in cubic feet per second. That's how much water is coming down the river. And these are dates along here, August 23rd, 4th, 5th, 6th, so on. So that, of course, is the big rise. This is, by the way, this is a logarithmic scale. So that's a really big increase in the amount of water coming down the rivers. And then, of course, that's because of the heavy rain that fell from the hurricane. So check that one out as well. Let me see what else I have that I think is really important. Well, the radar, I love to watch the radar. You can get there a lot of different ways. For example, radar.weather.gov. But usually I go right to the closest weather radar to us is on Long Island. It's about here at a station called Upton, UPTON. So if you just Google Upton radar or Upton NOAA radar, you'll go right to that site and you get a nice visual representation of the precipitation in the region. One thing to remember about radar, I think you know what it is. It's a microwave signal that gets sent out from the radar antenna. It scatters off raindrops and then comes back to the receiver. And from the time it takes for the signal to go out and back, you get the distance. And of course, from how the antenna was aimed, you know the azimuth angle, so you can figure out where that is. And it's put together in a nice map like this. This was taken just as as the front part of the cyclone was coming into southern New England. And you see this nice heavy rain shield out here. The eye of the storm is probably about here. There wasn't a very well developed eye, but the center of it was probably about here. And the backside was fairly dry, surprisingly dry. We'll talk about that later on. Some people think that it was transitioning away from a tropical cyclone to a different type of a storm at this point, but that's getting ahead of the story. But you can check, I check it frequently when I'm about to walk out to go someplace on campus, and sometimes I'll go onto the Upton radar and just check the radar to see if it's raining. I've got a window, but what I really want to know is not whether it's raining now, but is it going to rain in 5, 10, or 20 minutes? Well, if I see a big squall line coming towards New Haven, then I can decide whether maybe I can sprint to where I'm going before it gets there, or maybe I better just wait until it runs through, and then I'll walk out to my car or walk out to my meeting. So that is a very nice, in meteorology, we've got a funny word for that. We call it nowcasting. It's like forecasting, except it's forecasting for just the next few minutes. And the best way to do that is with the Upton radar, because that'll tell you, New Haven's right there, and it'll tell you if there's a little thunderstorm or something just about to move over New Haven. So it's very, very convenient for that purpose. Another great one, of course, is the satellites. And here's a picture of Irene. Now, there's lots of ways to get at the satellite data. www.goes.noaa.gov is one way to do it. And the GOES stands for Geostationary Environmental Satellite. This means it's a satellite that is it's over the equator, and it takes 24 hours to go around its orbit, just like the Earth takes 24 hours to spin on its axis. So it stays over the same point on the equator. So we say it's geostationary. It's like it's parked right up there, and it's the best satellite for watching cloud patterns develop and move, because you're not just getting an occasional snapshot when the satellite comes back around. No, that satellite is there and is taking a picture about every 10 minutes. So you get a really good way to follow the structure of these cloud patterns as they're swirling around. So there's a good example. Now, also notice these clouds are quite different than the ones up here. The radar showed that these were not precipitating, but these were. So the deeper clouds with the big anvils on them were precipitating, but these low-level clouds were not at that moment. Any questions on this? Okay, well, do I have anything else? Oh yeah, so this gets a little more techy maybe, but I love it, and that's getting the balloon sounding. So the National Weather Service launches weather balloons twice a day from a couple of hundred places around the United States and 400 or 500 around the globe. And they're all accessible. The balloons are launched at 0 and 12 universal time. You're going to have to become familiar with what we call universal time. Sometimes we call it Greenwich Mean Time. In the military, it's called Zulu time. We'll most of the time call it just universal time. And so 0 and 12 universal time, when we're on Eastern Daylight Time, like we are right now, would be 8 o'clock in the morning and 8 o'clock in the evening. So those balloons are launched at 8 o'clock in the morning, 8 o'clock in the evening. And they take about, they'll launch them a few minutes before that time, because they take a couple hours to rise. But if you go on to, what I usually do is go on to the University of Wyoming website, because they've got a really great website where you can get all the soundings all the way back in time. Back 50 years, you can get soundings from all these different sites. So that's a really handy one to go into. So what I did here was pull off the, I forgot to say, the closest Radiosonde site to us is also Upton, New York. Same place where that radar is. They launch balloons from there as well. So what I did here was to go on to the Upton, Wyoming site, pull down the sounding for as the storm was approaching, and then as it was leaving. So this is a balloon carrying a small instrument package. You'll be working with this kind of data later in the course. So this is a little bit of a preview. But what's plotted here is, well, I'll say altitude, but really it's pressure, because that's how we know how high the balloon is from the pressure that it's recording. Pressure decreases as you go up in the atmosphere, so it's a convenient way to keep track of your altitude. And then on this scale is temperature, and two lines are plotted. One's the air temperature, one is the dew point. So when they're close together, that means the air is saturated with water. So that's not a surprise that as this hurricane was coming over us, the air was saturated at least 3 or 4 miles up in the atmosphere. Maybe that's not saturated, but it probably is too. Probably that's just an instrument error or something to do with ice versus water. It's probably saturated all the way up. And then the winds are given over here in a traditional meteorological wind barb. It's a little feather that you draw with a little arrow with feathers on it, and the number of feathers tell you how fast the wind is blowing, and the direction tells you what direction the wind is blowing. So for example, here, the wind was, I think, 30 knots from the east. Well, that makes sense. That's when the storm was approaching. So here in southern Connecticut or Long Island, the wind was from the east. And then as the storm was moving away, we had 40 knots from the west. That was taken 12 hours later. 0Z on the 28th and 0Z on the 29th. That kind of brackets the hurricane passage. And then you can see this begin to dry out a little bit aloft. We saw those low clouds in the satellite image. That's this saturated area, but then it was drier aloft. So you can understand that vertical cloud structure we saw in the satellite image by looking at the balloon sounding. So this is great because this stuff is online all the time. And so whenever something's happening, not only here, but anywhere, go on to the website, take a look at it, and I'd like you to work with this raw data rather than just listen to what the weather forecaster has to say. Question, yeah.
Does it make a difference if those lines are like connected, like some of them kind of look like a flag, or like, or does it?
Oh, here you mean?
Yeah.
Yeah. So there's a little thick barb there. That's the 50 knot. So it's kind of like Roman numerals in a way. So that's 40. That's 55. A long, thick, and a short. A short is 5. A long is 10, and the thick one is 50. Okay. So it's kind of like a Roman numeral way of keeping track of wind speed. Yeah.
You said those two lines measure one's air temperature and one's dew point.
Yeah.
Is there a reason why the second one, like the first one goes all the way up, and the second one, like one of them kind of stops there?
Yeah, probably it got so dry that the sensor could not accurately measure. So they probably just stopped the data because it was getting too dry. We were getting, as that cyclone moved away, we were getting cold air coming in behind it, descending down from Canada, and that was very dry air. And you're getting a hint of it, but then I think the sensor probably couldn't keep track of the real dry air behind it. It's not a perfect instrument. Be aware of that. Whenever you're looking at real data, you know, it's not necessarily always going to be perfect. Other questions on this? Okay, well, let's see what else we have to do today. Well, okay, so I've gone through all of the things that I wanted you to be aware of as sources of information, and I think there's just a couple other things I want to do today. Oh, I wanted to, before I forget, I wanted to say a couple words about myself, because some of you may be curious to know what I do, and although it may become obvious as the semester unfolds. But so I started out in, when I started college, I had no idea I was going to move into geoscience or geophysics or atmospheric science. I was interested in airplanes. I wanted to fly airplanes. And so I got an undergraduate degree in aeronautical engineering and a master's degree in aeronautical engineering. I thought I was going to be a military pilot. And then things developed in a way that made me realize maybe that's not my career goal after all. So I switched. I went in the Navy for 3 years, spent some time on ships. And during that 3 years, I realized I was really more interested in the atmosphere in which the airplanes fly and the oceans than I was in the airplanes themselves. So as many of you will find, the careers you have in mind right now may not be the ones you end up with, because as you have new experiences, you realize there are other interesting things to do out there. And so just be flexible and keep your options open. So when I got out of the military, I went back to school then in geoscience, study of the Earth and its atmosphere and its oceans, and developed a career there. So my interests today are primarily in what I call regional climates. How does a climate in one part of the world differ from a climate somewhere else? Does that have to do with just where it stands on the Earth, its latitude, its longitude? No, it also has to do with local features in the land, coastlines, mountains, land surface structure. So these are the things that I'm interested today. I've done projects many places around the world trying to understand how the local climates in those regions work. So you'll find as I go through the course that I'll be occasionally referring to some of the work that has been done in that area. Are there questions? Okay, well, you're not going to get away today without a little bit of lecture. So I wanted to run through one argument, I think we have time for that today, that will, I think is important for forming a foundation for everything else we do in class. And so I'm going to address this one question. What is an atmosphere? My answer is going to be that it's a layer of gas held to a planet by its gravitational field. That's my definition of an atmosphere. And I want to illustrate this by doing what's called a Gedanken experiment. A Gedanken experiment is a thought experiment. Comes from a German word for thought. So we're not going to actually do this experiment. We're going to think our way through it. So here is my little Gedanken experiment. I've got a planet here. It has some mass, m. Has no atmosphere. But I've got an alien. I've hired this alien to bring it an atmosphere. And he's over here, and he's got a box of air. And the molecules are there. And he's far away from Earth, so it doesn't feel the gravitational field of the planet yet. And so these molecules are going to be uniformly distributed through the box. They don't feel the tug yet from the planet that's going to maybe want to squeeze them towards this corner of the box. They're too far away for that. So they're just sitting there freely bouncing around in the box, having a good time. Then we bring that box down to Earth. We set it there for a minute. Well, now it feels the gravity field of that planet. Now the molecules are still moving around, they're bouncing, there's pressure in that gas. But the gravity field is going to play a role too. So more of those molecules are going to sink to the bottom. There's going to be a few up here at the top, but most of them are going to be down at the bottom simply because of that gravitational field. And then the final step of this experiment is I'm just going to open a door there. When I open the door, that gas is just going to flow right out. The box is going to become empty, and I'm going to have an atmosphere. Obviously, it's held to the planet by that gravitational field. Just like it was in the box here, there's going to be a few more molecules down below and fewer up at the top. So you're going to have that gradient because of the gravity field. But basically, it's going to be held there by the gravity field. So that's what I mean by layer of gas held to the planet by the gravity field. Now, a couple of things that I've already misled you about. First of all, of course, that isn't how planets get their atmospheres. They're not brought in by aliens. There are two leading theories for how a planet really gets its atmosphere. One is that it is a so-called primordial atmosphere. That is to say, it was formed with the condensing planet. Formed with the condensing planet. When the planet was first formed, it was formed from material out in space that was collected together gravitationally, kind of a gravitational inflow. And at the same time, there would have been lighter molecules out there that didn't want to become incorporated in the solid planet surface, but they would have been attracted to, and so you would have formed the solid atmosphere from the heavier compounds, or the ones that like to bond together, and the lighter molecules, or the ones that don't like to bond together, would have formed this envelope of gas around it. So that's one possibility. The other is that, well, maybe there was an atmosphere formed in this way, but maybe it was lost. After all, the Earth is almost 6 billion years old. So whatever atmosphere it had at the beginning isn't necessarily the same atmosphere we have today. We'll talk about that next time. But even if the planet, if the atmosphere was never there or was lost, the planet could still, over geologic time, give off additional gases from its interior. I'll just call that outgassing. Outgassing. For example, if you go to a volcano today, you can measure gases coming out of the planet into the atmosphere. So this is an active, dynamic, ongoing process where gases come from the interior of the planet out into the atmosphere itself. So either one or some combination of the two is where the Earth and the other planets actually got their atmosphere from. Now, I've misled you in another way, too, the way I've drawn that. I've drawn the atmosphere relatively thick, that distance. If I call the radius of the planet capital R, and the thickness of the atmosphere, let me call that little d, I've drawn them with the ratio of about 5 or 6 to 1. Actually, the ratio is much smaller than that. If I take the ratio of d to r, for the Earth, the radius is about 6370 kilometers, whereas the depth of the atmosphere, it's a little bit hard to define the depth of the atmosphere because it has a gradual top. There isn't suddenly a level where suddenly the atmosphere stops, but I'll make a rough estimate and say 100 kilometers. So that's a lot smaller ratio than I've drawn there. In fact, probably more like the thickness of my pen line would be a more accurate representation of how thick the atmosphere is relative to the planet itself. Questions on that? Yes?
Is like the ratio of the thickness of the atmosphere to the planet stable, or are we like constantly losing gas?
We are. I'm going to talk about that next time. I'm going to talk about the loss mechanism, and we're going to compare the different planets, some of which have lost all their gases, some of which have retained some, like the Earth, and some of which have retained almost everything, like Jupiter. So we're going to put that into a context next time. Anything else? Okay, well, I want to address this question then. We've done that one. The Earth's atmosphere is made primarily of nitrogen, oxygen, and argon, a little bit of argon. And all three of those molecules are constructed in such a way that they do not absorb light in the wavelength range to which our eye is sensitive. In other words, air is invisible to us. That's interesting. So then how do we even know there is air? If we can't see it, how do we know there is air? Someone want to suggest a way that we know there's air? Yeah.
For breathing.
Breathing. That's a really good one. Yes? Friction.
Like friction against objects and how those objects.
Yeah, for example, let's say I've got this piece of paper and I drop it. It falls very slowly. If there were no atmosphere, of course, it would fall faster than my pen with a clunk, well, no, there wouldn't be a clunk, would there? Right, there's no sound, right? The sound is transmitted through the air, so if there were no air, you wouldn't hear me speaking. That'd be good, or you wouldn't be able to hear any noises that I'm making up here. What other ways do we know that there's an atmosphere? Yeah.
Pressure.
Pressure. How do you know there's pressure?
Well, when you're up, like, I guess it relates to breathing too, but
Relates to breathing.
mountains, it's harder.
Right. Is there something you're going to do today? Think about this pressure thing. How do we sense atmospheric pressure? We can have an instrument that does it, but how do we sense it? Yeah.
How difficult it is to breathe.
Well, not so much, because remember the pressure is here, but it's also here, right? So it's kind of equalizing in a way. All we have to do with our lungs is to produce a little bit of difference between what's here and what's here, and we can breathe in and out. You could change the absolute pressure by a factor of 2, and that wouldn't change. You'd still be doing pretty much the same thing. But there may be some other ways in which you would notice pressure, yeah.
Like your ears, like sinuses?
Ears, yeah. So if you've got a sudden change in pressure, for example, when the aircraft is beginning to descend, then you might feel it in your ears as well. I remember when I was in the Navy years ago, first part of flight training school, they wanted to show us what it was like to have a sudden decompression, right? Sudden decompression. So you're flying along in an aircraft, window pops out or whatever happens, suddenly you have much less air in the cabin. So they took us into a room about the size of this area here, and there was another chamber next to it with a big pipe connecting the two. So what they did, they closed the valve in the pipe, they pumped down the other chamber, and then all of a sudden they opened the valve. So half of our air went over there. So what do you think happened? What was it? Just imagine, let's do a Gedanken experiment. What do you think we noticed, or what happened to us when we did that? Any guesses?
Body nose.
Sorry?
Body nose.
No. No, my nose didn't bleed. Other guesses?
Ears popped.
Ears popped, yeah.
I got a little lightheaded.
Yeah, that came later. Okay, so the first thing that happened is the air turned white. You couldn't see anything. Why was that? Well, when the air, we're going to talk about this at length in the course, but when the air expands like that, it cools, and a cloud formed in our chamber. So just like that, and that happens, by the way, extremely fast, like in a fraction of a second, you've got a very thick cloud in there. So that was the first thing I noticed. Then this gets a little bit indelicate, but the next thing that happened is we all began to, let's use the word outgas, for lack of a better term. So we kind of leaned over a little bit in our chairs and we outgassed for a while. And then we began to feel faint. So what they had us doing was writing out our name over and over again. So later on, we could look and see what we had written. Of course, you write it the first few times, it looks okay, and then it begins to scroll, and then you lose consciousness, and they bring the air back up. So that's some sense. So I guess a follow-on question would be, and related to the first, would be if we suddenly lost all the air in this room, what would kill us first? What would kill us first? It may be closest to your answer, actually, but it won't be exactly that. What would kill us first?
Lung.
The lung, yes. So any scuba divers in the course? What do you worry about when you've been diving deep and you come up suddenly?
Expansion of gas.
Bends. It's called the bends, right? That's it. So what's happened is when you're scuba diving, you're down at a high pressure for a while. Nitrogen dissolves in your blood at a higher fraction than it is normally. Then when you suddenly come up, that gas bubbles out of solution, like taking a can of Coke and shaking it, basically. the gases come out of solution, forms bubbles, and of course then you've got bubbles in your bloodstream. So that's the benzene. You can die from that, and it's kind of like having a stroke. That would probably be the thing that would, basically, your blood boils. That's probably the best way to think of it. You've dropped the pressure so suddenly that then the gases that are already in your bloodstream just suddenly begin to, it would happen in an instant. And you would be in excruciating pain, and then you would be dead. So that would, what would happen? Okay, so that's probably first. What would happen next?
Question on that.
Yeah.
Is that like what happens when like an astronaut depressurizes in space?
Right, if an astronaut, so an astronaut is in a pressure suit for just this reason, right? And if you were to develop a leak in that, and he was to lose his pressurization, he would die just like I've described, instantly and in great pain because of the blood boiling, basically, all the dissolved gases coming out of solution. So the pressure, you mentioned the pressure does that for us. It keeps those gases in solution, and if you suddenly release it, out they come. The breathing was mentioned, so we couldn't breathe, and that would knock us out after, what? You can hold your breath for a minute or so, but then you might become unconscious after that. Some other things would take a lot longer, so they're not really relevant. You're dead, but some other things that would be probably good to write down would be the atmosphere has a great moderating influence on our climate, as I'll show later on. Were it not for our atmosphere, the temperature of the surface of our Earth would be much, much colder than it is, colder than we could survive. That's a long-term effect, but the atmosphere is very important for that. And the atmosphere protects us also from X-rays, ultraviolet radiation, small microparticles coming into the atmosphere. They burn up in the atmosphere. So the atmosphere has a great protective role to play in allowing us to exist on this planet. So we're exactly out of time, and I'll see you next time. See you on Friday. I'm Professor Ron Smith from the Department of Geology and Geophysics, and if you're in the right place, you know that this is the course called The Atmosphere, the Ocean, and Environmental Change. There's a lot to talk about today. Some of you are shopping. I want to be sure you get enough information about the course to make your decision about whether to take it or not. And for those that are definitely in it, I want to get you started towards some of the course material that we have in this course as well. So as I will usually do in the mornings, I'll have some notes in the upper left there, and I want to run through some of those. This is just informational stuff, logistical information about the course. There was some confusion about this. The lab is required. So everybody that takes this course takes the lab, and everybody that takes the lab takes this course. You get graded separately for the two, but the two are really, the subject material is merged and coordinated in a certain way, so you have to take both of those. That means when you're signing up for the course, be sure to sign up for the lab as well. It has a different course number. For example, EVST 201 is this course, 202 is the lab. Or if you've signed up under geology, it's 140 and 141 is the lab. Now, we also, the classes server, they're separate sites, so be sure to register on both of those, because I'll be posting information about the lab on the lab course number. Now, the labs aren't going to start actually till week 3, so we're not going to do lab section signups yet. But I will tell you that the labs are on Monday and Tuesday afternoons. There's with an elementary knowledge of high school physics, and I'd like to get you started on that, both because we need you to be fresh and familiar with those subjects, but also those of you that don't have a good background might want to use that as a guide as to whether this is the right course for you. So take a look at that problem set as soon as you can, and if you have any problems with it, talk to me, talk to your TAs. Speaking of TAs, let me see if I can introduce them to you. Ravi is there. Jennifer is there. Is Meng here? Meng is right there beside them. And Srikanth. No Srikanth today. Okay. And by the way, Melanie here on the left, on my right, is going to be helping with the taping transcripts. So we're going to have this course taped, 4 sections altogether, and you've got to be able to fit into at least one of those, and we hope more than one, because we're going to have to even you out. But those labs are at 1:30 and then at 3:30 on both of those days. So we'll be doing those lab sign-ups next week when you have a better idea of what your schedule is like. But try to keep those Monday and Tuesday afternoons open so you can fit into one of the labs, because if you can't take the lab, you can't take the course. Let's see, there's already a problem set posted on the classes server, and it is due next Friday, a week from Friday. And you may ask, how could I have already posted a problem set when I haven't given a single lecture about the course? Well, that's because this particular this particular problem set is kind of a warm-up. It's got questions on there that you can do, and I'm afraid they're not going to be, these tapes are not going to be available to you during the semester. There's too much of a lag time, I think, to get those to you. But I don't think it'll be a problem in class. One thing I want to mention, though, this course, well, it seems like we got a pretty big class here, but still, even with this class, it's a very convenient room and a very convenient class to have a lot of discussion, questions, answers, and so be prepared for that. Don't be shy about asking questions, and I think that'll really add a lot to the course if you get in the habit. If you've gone for a period or two and haven't asked a question in class, you should ask yourself why, because it's probably not the clarity of my lectures. It's probably that you're just reluctant to put your hand up. So try to gauge this a little bit. And if you're asking